Welcome. Today's notes worksheet is entitled Logarithmic Properties. We'll have the opportunity today to make the distinction between what works numerically with logarithms and what does not work numerically with logarithms. You will definitely need a graphing calculator for this lesson, so please have one handy. And then I think what we'll do is go ahead and start it out here by tying up a couple loose ends from the previous day's lesson, just kind of talking about logarithmic functions, in this case a very specific logarithmic function. And then we'll get into, obviously, the properties that you see on your paper here. So at the top it says the natural logarithmic function is, and so let's jot this down and then kind of talk about how the mathematics works. So it's the logarithmic function in base e. So we talk a lot about exponential modeling using that base e. And so as a result, what we want to do is to have the natural connection to its inverse. And the inverse of an exponential function would, of course, be the logarithmic function in the same base. And so what that would look like in just its most basic form, here's the exponential function in base e right here. And again, the most basic one that we can come up with is just y equals e to the x. So there's that transcendental number used as the uniform base for exponential models. And then if we were to go ahead and take a look at its inverse, well, let me come over here for just a second. And as a matter of fact, don't write this on your paper. But if I was to ask you to find the inverse of that exponential model, you would, of course, switch the x and y, and we would get that right there. And then if we would put this in explicit form, meaning we would solve for y, we would take this e right here and roll it on over to the other side. And so it rolls nicely. We've kind of talked about that little skill set. And of course, the y would drop down when that e rolls over. And as that e crosses the equal sign there, it changes, of course, from the base to this power to the base of a logarithm. And so this would read log base e of x, which we would write as the natural logarithm of x. And so you can kind of see then that this becomes the inverse of this right here. Well, let me just do a little erasing on that piece and then just kind of write that in, that this is the inverse of our exponential model in base e. Okay, so we've got those two pieces. If I graphed this function and this function on the coordinate plane, we would obviously see the perfect reflection over the line y equals x. We would see all the characteristics that go with inverses, of course. All right, nice. Well, let's get into some of the properties here. There's some that we'll take a look at. Obviously, the number one, the product property, is one we'll see quite a bit of. And again, we'll get an opportunity to kind of sort of look at that with computation and then also do just a very quick proof on that just to see if that it works out nicely. So here's what I have. Product property basically states, and I'll look at the left-hand side first, that we can add two logarithms together in the same base. Notice the same base. So we can add two logarithms together in the same base by combining their inputs with a product. So take a look at that piece right here. Add logarithms together by combining them with multiplication. And if you remember, it's kind of very similar to one of the exponential properties that we saw at the very beginning of the year. And this would look something like multiplying powers with the same base. We add the inputs, we add the exponents. So let me try to phrase it properly for you, and then we'll go ahead and confirm this with the calculator. But basically, with exponents, we can multiply powers with the same base by adding the inputs. Now, the exact reverse of that would be adding logarithms with the same base by multiplying the inputs. Does everyone see that piece? Pretty much the exact opposite of what we have here. And that is the relationship, of course, between exponential properties and logarithmic properties. Okay. Well, let's go ahead and confirm a couple. So log of 24, what I'm going to do is kind of go right side to left side here, obviously being an equation. They are in perfect equilibrium, so I'm going to go ahead and work with the right side of this a little bit and then kind of change it to the left side. So I'm just going to pick any two numbers that multiply to 24 just to kind of keep that input as a 24 here. So like 4 times 6, something like that. Obviously that would be log of 24. And what this is basically stating is this can be expressed as the sum of two logarithms, log of the first input plus log of the second input. So that should be the case. Log of 4 plus log of 6 should be log of 4 times 6. So let's go ahead and just check that out quickly here. And I'll grab my calculator. just easy to stay in that common logarithm base, so base 10. And so log of 24, there's our number, looks great. And if I was to take log of 4, close that off, of course, plus log of 6, and I should get that exact same number. Now, I guess I would have a question for you. Would this work with any two numbers that multiply to 24? Could I do something like 3 and 8 right here and do log of 3 plus log of 8? Could I do 2 and 12? 2 times 12 is 24, so can I do log of 2 plus log of 12? Yeah, let's just check it out quickly. We have a moment. So let's do the 3 and the 8. So log 3 plus log of 8, because 3 times 8 is 24. Notice, same number. How about 2 and 12? So 2 times 12 is 24. So log of 2 plus log of 12. And notice, of course, still the same. Wonderful. So I hope everyone kind of sees that piece. You can add two logarithms together by combining those inputs with multiplication. So log of 4 plus log of 6 is log of 4 times 6. And there's obviously your log of 24. Let's just choose another one here. Let's do log of 54. So here we go. I have a log of, I don't know, let's just do 3 times 18. Something like that. So 54 is made up of a product of 3 times 18. That should be now log of 3 plus log of 18. Let's go check it out quickly. We've got that moment here. Let's do it. So log of 54. Nice. Got that nice decimal right there. And what that should be equivalent to is log of 3 plus log of 18. And again, that is because 3 times 18 is 54. And notice it's the same thing. Would it work on, say, 9 times 6? So log of 6 and log of 9, because 6 times 9, 54. Obviously, you can see any combination under the sun would work. So it's kind of an interesting piece here. Sorry for the redundancy, but I love seeing that connection. So remember, just way back when, multiply powers with the same base, we add the inputs. So the exact opposite would be adding logarithms with the same base, we multiply the inputs. And that's going to work out nicely. Let's do just a very quick proof of that, so to speak, just to kind of see that it does work algebraically. This will be the only one that I'll go ahead and take a moment to prove. All right, so it says proof of product property. And I'll go ahead and define a couple things up here, and then we'll get it rolling. So we've got m and n, which I'm going to go ahead and define for us. So on your paper, if you don't mind, just kind of write this piece. M is going to be a power in base A. And as a matter of fact, just to get this moving along here, if I was to kind of convert this to its logarithmic form, I'd roll over that A. And so what that basically means is the x would drop down. And so x is equal to that right there. Again, just this would roll over, x equals log base A of m. And then one other thing I'm going to go ahead and define. I've got to get n going here. As you see, there's m and n. And so in this case, I'm going to do this piece. N is equal a to the y. And what that would mean, of course, if I kind of changed forms on you here, bring over the a. So that means y is equal to log base a of n. We'll see both those forms come up, so just wanted to keep that together for us. All righty. Now, guys, what I'm going to basically do is take the right-hand side of this equation and make it look like the left-hand side to show that they're equivalent. So here we go. Everyone, if you would, on your paper, just write log base a of m times n. That looks good. Now, guys, as you can see, just the way I defined a couple things, I'm going to do a little substitution here. So this is going to go in for m. This is going to go in for n. And let's see what unfolds when I do that. So m, as I stated, is a to the x. N, as I stated, is a to the y. Okay, so I just had two things equivalent to these powers in base A, and I use substitution there. Now again, remember, these things are intertwined. This right here is an exponential property just ready to be had. Can I multiply two powers with the same base? Yeah, of course. I add the exponents. So this is a to the x plus y. Okay, very nice. Now, if you look at this piece, this logarithm is actually equivalent to something quite simplistic. If I asked you to evaluate this, you would ask yourself, a raised to the what is a to the x plus y? That would be how we would look at it. So the value of this logarithm is the exponent in this base that will give us this piece right here. So a to the what is equivalent to a to the x plus y. And as a matter of fact, the answer actually happens to be just x plus y. So this logarithm right here simplifies perfectly to x plus y. And then take a look, of course. You see the way that I had transformed these two things right here. Everybody, isn't that x? And isn't that y? And so as a result, x is this, and y is this. And we've got our winner. So you can see that what we started with, which happened to be just the right side of this property equation right here, is equivalent to the left side, of course. All right, so again, just a little algebraic technique in order to just show that those two are the same. And obviously, we showed it on the calculator. All right, well, let's move it along and get a couple of the other properties taken care of, and then do a couple examples as well. So the second one, of course, is the quotient property. So as we saw, when you add logarithms with the same base, you multiply the inputs. Well, very simply, shouldn't come as a shock here. When you subtract logarithms with the same base, you divide the inputs. That's how this works. And again, it's very similar to this. Obviously, this is what's used to produce this up here. So let me just go ahead and run through the verbal jargon. So basically, with exponents, when you divide powers with the same base, you subtract the inputs. Here, when you subtract logarithms with the same base, you divide the inputs. Obviously, the opposite. So let's go ahead and just confirm it on the calculator here. Let's come up with a quotient in order to get 9. So give me any two numbers, really, that divide to 9. I'm just going to go 18 and 2, keep it simple. So that would be a quotient of two terms in the input of our logarithm. And what that should be equivalent to is the difference of those two logarithms using those two values as the inputs. So I'm hoping everyone sees this piece right here. Subtracting two logarithms is the same as taking the inputs and providing a quotient there. Well, let's go ahead and check it out. So log of 9, no big deal. There it is. And that should be equal to log of 18 and then minus log of 2. So again, 18 divided by 2 is 9. So as a result, the difference of the two logarithms is the same. Could I do 27 and 3? Any two numbers that divide to 9. So 27 divided by 3 is 9. And so as a result, log of 27 minus log of 3 gives us the same as log of 9. No end in sight, right? Okay, cool. Let's just do one more here. So log of 12, let's come up with the quotient there. I don't know, how about 36 and 3? Something like that would do. And I think we've got it at this point. So this is going to be log of 36, and of course, just minus log of 3. So again, difference of two logarithms. All right, so we've got the quotient property taken care of. Let's move on to the next piece, which of course would be the power property. And so this one states if we have the exponent as part of the inputs of the logarithm, that value can actually go out in front, as you see right here, as a factor in front of the logarithm. And again, it uses the power property of exponents to kind of produce it, very similar in nature. If you remember power raised to a power, we multiply those inputs, and here you've got the multiplication used as the power right there. Okay, so let's go ahead and take a look at maybe this piece right here, make a connection or two, and then move on to the examples for the day. So can you come up with the number 8 as a power? And the way I saw this, 8 can be written as a power base 2, in this case 2 to the 3rd. So 8 is really 2 to the 3rd, and what this states again is if there is an exponent as part of the input of the logarithm, and that's what this is right here, then this can go right out in front, and it should be equal to 3 times log of 2. So a factor out in front. Very cool. Well, let's go ahead and obviously check that out. I will go ahead and do log of 8 right up here, and you get that piece. Now, theoretically, that should be equivalent to 3 logs of 2. So 3 times log of 2, and notice we get the exact same answer, of course. So again, the exponent can come out in front as a factor. Just one thing to note on this, just always trying to make connections for you, make it sink in a little more. But think about what 3 log of 2 really means. So this is 3 times log of 2. And remember, guys, multiplication is really just repeated addition. So when I say 3 log of 2, isn't that what it is right there? And look at the top of your page, of course. Do we have something that allows us to add logarithms together in the same base? Well, we sure do. We multiply the inputs. So isn't this just the products property kind of taken to the next level? Log of 2 plus log of 2 plus log of 2 is log of 2 times 2 times 2, or of course, log of 8. So you can see all of this is really intertwined perfectly. Okay, very cool. Log of 36, let's just do one more on the calculator there. 36 as a power, how does 6 squared sound to you? And of course, just kind of looking at this piece, this number can go out in front and it becomes 2 log of 6. And so, same deal as before. I'm going to go ahead and type in log of 36. Get that right there. And then that should be equivalent to 2 logs of 6. And there it is. All right. So I hope just having the calculator confirm all these numerically, it just hopefully makes that distinction. This works numerically. This does not work numerically. So everyone, let's just do a couple examples. There are some pretty standard examples that go with a lesson just like this, just manipulating logarithmic expressions. So we'll do kind of a back and forth situation. We will expand and then condense. So let's do example 1 here. And let's see if we can extend this out into multiple logarithms. So guys, very simply, we've got log base 5 of 3 times y squared divided by 4. The way I read this, and I do this a lot myself, is I see this input of the logarithm right here, circling it on my board, is made up of 3 different terms essentially. So I'm going to circle those terms. It helps me really get my bearings. So that's one term in the input of the logarithm. That's another term in the input of the logarithm, and that's a third term in the input. Now, you could just do that very, very lightly, but the thing that strikes me is as soon as I recognize that there are 3 terms making up the input of the logarithm, when I expand this out, everybody, that means I'm very simply going to have 3 different logarithms in our base. And so as a result, I'm going to have log base 5 of our first term, so log base 5 of 3. Now here's where you need to come in. With this product right here between these terms, when I extend that out, how does that translate, everybody? Is it the sum or is it a difference? And again, product property means that we add the logarithms together. So I would have that. That's how that translates right there. So product translates to an expansion using a sum. All right, and then quotient, so divided by that 4, if we're going to take that 4 and give it its own logarithm, it's done with a minus symbol. It's done with the subtraction. So as a result, log base 5 of 4. And that's how that plays out right there. 3 logarithms. Again, product property, sum, quotient property, translates into a difference. Probably one more thing we can do here, so I'm going to get that going. I hope everybody recognized we do have an exponent as part of the input of the logarithm, so that number should go out in front. So I would just translate this as log base 5 of 3, 2 log, I forgot a base 5 there, log base 5 of y, and then minus log base 5 of 4. That looks great. Okay, I'm going to box that up just to make sure that's our final answer, and then we shall get on to the next one. Letter B, just log base 10 here. And same deal, I look at my input of the logarithm, and it seems to be really primarily made up of 2 different terms. So just very lightly on your paper, circle those two terms exactly like I did, precisely there. And what that means to me is essentially when we expand this out using our properties, we should get two different logarithms. So let's do it. Let's attach a logarithm with that first term in the input. So I would say it's log of x. No big deal right there. Now the question is, as this input is made up of a product of these two, how does that translate upon expansion with the sum? And so I should get log x plus 1. All right. Now the question I guess I would have for you is, are we done? And I would say no, not yet. So remember, there are different ways to represent certain values. And what I'm after in this case is that there are two different ways really to represent roots. In this case, we have it in radical form, square root of x plus 1. But remember, these roots can be represented as exponents. So square root of x plus 1, if you remember, can really be represented as x plus 1 raised to the 1/2. And that's the key, seeing if you remember that piece. So don't forget, roots can be represented as exponents there. And this is the base raised to the 1/2 power. And now when we do that, guys, what happens to that 1/2 as it is the exponent making up the input of this logarithm? It comes out in front. So log of x plus 1/2 log of x plus 1. Please make sure you have parentheses around that piece. Otherwise, actually, it would not quite be the same. This, as a matter of fact, is our answer. And it looks great. Now, here's one thing to note. There is what's called a product property. There is what's called a quotient property right there. Is there a sum property? If you don't mind, let's just take 30 seconds and do a quick investigation. I would ask you this. Is this the case? Can I expand that out even further? Does that work numerically? And again, part of what we're doing today is just things that work numerically with logarithms, things that don't. So let's see. I'm just curious myself here. So let's do log of, say, 2 plus 3. That would be something like this right in here, a sum in making up the input. Is that equal to log of 2 plus log of 3? And look at the answer. No. So is this the case right here? Absolutely not. So there is what is called a product property. There is what is called a quotient property. But guys, there is no sum property and there is no difference property. In fact, we probably had this exact same discussion when dealing with exponents. Beautiful. All right, so by the way, that's as far as it goes. So when you have a sum of terms making up the input of the logarithm, that's the quantity right there, guys. Don't touch it. All right, let's go get letter C. Moving on over here, I have two terms making up the input of the logarithm. That's how I see it. So I'm just going to lightly circle those two. And of course, that means really two logarithms. So log of cube root of x minus 2. What do you guys think in this case with this quotient right here? Plus or minus in between the logarithms? Minus. And log of x plus 2 raised to the 4th. If you can do this a little faster than I can, great. You know, more power to you. But I'm going to go ahead and take this in a couple steps. Again, cube root is really, can be represented as an exponent. And so I have that piece right here. Just acknowledging that x minus 2 to the 1/3. And now, guys, of course, those exponents come out in front. Please, again, parentheses around that x minus 2. And then same deal here. 4 comes out in front. Parentheses around the x plus 2, please. Again, if you don't have parentheses, you know, theoretically it's actually not correct. Order of operations would be different, and so it's a different expression. Okay, 3 good ones for example 1. So on to example 2 then. Let's reverse course here. So example 2 states condense the expression into a single, and notice I underlined it for you there, So we're looking one logarithm, everybody, just one logarithm in whatever base we're looking at. And again, let's just reverse the example 1. So here we go. I've got 3 log of x minus log of y plus log of z. And the way I read this, guys, is 3 different logarithms. And so when I condense this expression into a single logarithm, so 1 logarithm base 10, I see the input being made up of 3 different terms. So 3 logarithms should condense down into 1, but the input of the logarithm should be 3 terms. So what I do is I just kind of make my parentheses there to make up the input of the logarithm. And let's go ahead and take it. So a couple things here. I'm seeing the power property in action, everyone. So see the 3 out in front of the logarithm. What we did is brought it out in front in the previous example. So what I'm going to do here is bring that up as the exponent for that particular term right there. And so what I see is we've got an x cubed going on. So that is one term making up the input of our single logarithm right here. Wonderful. Now look at this piece right here, everyone. So notice, subtracting logarithms, how does that translate? Well, the subtracting logarithms is the quotient property. And so in this case, what we're going to go ahead and do is create our division symbol right here. And then it looks like I've got 2 terms, because of those 2 logarithms right here, going to make up the other 2 terms in the denominator of this input. And so as a result, what I see is we've got minus the log of y. So we take this input right here, and it becomes one of the terms of our input. And then here, guys, of course, is the product property. So adding logarithms together means I take the terms of those inputs and I multiply them together. And that's how it's going to pretty much look. So 3 logarithms translates into 3 terms when we condense it into a single logarithm. All right, let's see if we can do this one. Same deal. So I got one big natural logarithm right here, and I've 3 different logarithms initially in the expansion. So what that means to me, of course, is we're going to go ahead and put 3 terms making up the input of our single logarithm right here. I think that's how it's going to play out. Let's just go ahead and reverse course on these numbers right here. They become the power. So remember, this is going to be 3x plus 1 to the 1/2. And please don't forget that raised to the 1/2 is actually a square root. So I'm going to write it like that right away. And then I've got a difference between these 2 logarithms. So that is according to the quotient property. So I go ahead and make my little division symbol right there. And this 1/3 goes on up, and this becomes 2x minus 1 to the 1/3. Something raised to the 1/3, everybody, is cube root. So cube root on that. So cube root of 2x minus 1. All right, so 2 terms taken from these 2 logarithms right here. Now we need the 3rd. And here's how this one plays out. And it's actually very similar to the last one. It's just written in a slightly different way. But basically, I have another difference right here of this logarithm. And how that translates, everybody, is within the same fraction. And you can keep the same fraction here. I end up getting just another term down in the denominator. So as a matter of fact, it's just times that x down below right there. And I'll try to kind of convince you on that piece, and we'll create a little shortcut with this. But essentially, the idea being is anything that's a positive in front of the logarithm, that term goes to the numerator of our fraction. Anything with a minus or in front of the logarithm, or a negative, that term goes to the denominator. And you see that right here. This one comes down right here. This one also comes down right here. I've seen students try to do this in a little bit of an unsimplified version. This is actually quite a bit better. I like this. Okay, so let's just quickly talk a shortcut on this, and then I'll move on to the next piece. So one of the things that I would say is just anytime we have a positive in front of the logarithm and we condense, that term goes to the numerator. Anytime we have a negative in front of the logarithm, very simply, that term goes to the denominator. And that's what we saw right up here. So let me just kind of show you why that is. Here's just one very simple. I have a minus, or a negative symbol in front of the logarithm. And if it helps you just for a moment, I'm going to throw a little -1 in there. So obviously that negative, or that minus in front, is really like a -1 as a factor in front. And guys, if you look at this for just a moment, doesn't this -1 really represent the exponent right here using that power property? So what happens is that -1 goes up, and it becomes x to the -1st. And think about this, because as I said, all this stuff is beautifully intertwined. Very simply, haven't we dealt with negative exponents before? And when we've dealt with negative exponents, haven't we always tried to make them positive by moving them to the other part of the fraction, in this case bringing it down? So isn't x to the -1st 1 over x to the +1st? And so you can see this beautiful thing in action here, everyone, where basically this term goes to the denominator of the fraction. And that's exactly what happened here. This term came to the denominator of the fraction. So just trying to highlight here why in this problem, very simply, if there's a positive in front of the logarithm, the term goes to the numerator. If there's a negative in front of the logarithm, the term goes to the denominator here and here. And you can keep it that simple. And again, this was just to kind of show you why that works. All right, very cool. Let's see if we can get just on to the next piece and then start to bring this to a conclusion. So what we need to start doing is be able to evaluate logarithms in any base. And so I've got this piece right here that we'll investigate and then get our change of base formula going, and should bring us closer to what we're looking for as the goal of our lesson. So guys, here's what I'm going to ask us. Log base 2 of 7, it equals some number. So guys, put a little x, if you would, just on the back side there. And remember what we're asking when we do this right here. When I'm asking you is log base 2 of 7, what I'm basically saying is 2 raised to the what power equals 7. Well, I don't know that off the top of my head. I mean, I know some good powers of base 2. And again, you don't have to write this, just kind of thinking out loud. You know, 2 to the 2nd is 4. 2 to the 3rd is 8. So 2 to the something is equal to 7. Obviously, something in between 2 and 3. Again, I don't know what that is, and I want the calculator to be able to give it to me. So here's how we're going to do this, guys. I'm going to try to figure out a way algebraically to make it happen. And so, guys, what you're going to do is our nice little skill from one of the previous lessons, bring that 2 on over to the other side. And when you do that, of course, you get this piece right here. Okay, those two are identical equations, one in logarithmic form, one in exponential form. Now, everybody, here is what I'm going to do to both sides of this equation. I'm actually going to take the common logarithm to both sides. And again, that is perfectly legitimate, of course. Just what I do to one side, I do to the other. Good. Now, does anything strike you here? Look at the right-hand side and look at this x. Is there anything I can do with that x now that I have all these properties under my belt? Well, if this is the exponent making up the input of this logarithm, hey guys, it can go out in front. And so I get this piece right here. And wasn't I trying to find out what x is equivalent to? Isn't x equivalent to this piece right here? And now I have a beautiful way to represent it. Hey guys, divide by log of 2, and you get log of 7 over log of 2. And so now we have a way, using the buttons on our calculator, to evaluate this piece right up here. Log base 2 of 7 is log of 7 divided by log of 2. Let's go ahead and take a look at that. What did I say? It's got to be somewhere in between 2 and 3. Well, here we go. Watch this. Log of 7 divide by log of 2. And what did I say? Somewhere in between 2 and 3, probably closer to the 3, and that definitely bears that out. How cool is that? So let me just write a couple things in here. It looks like in this particular case, it was an example. It does say evaluate log base 2 of 7, and I just did that. So this is about 2 point, I think I caught about 807, somewhere in there. And the last one right here, of course, change a base formula, and take a look, everybody. So log base a of m, very simply, guys, you take the log of the input divided by log of the base. Now, theoretically, everyone, could I have done if you go back to this proof right here, instead of the common logarithm of this step, could I have done ln on both sides and come out with this in the end? Yeah. So I typically will do it as the common. I typically just do it like this. But just so you can see it, what if I did ln of the 7 divided by ln of the 2? And notice you get the same exact answer. So this property works absolutely wonderfully for those that have a TI-83 calculator. So if we need to evaluate the logarithm in any base, very simply we take the log of the input divided by the log of the base. Those who happen to have a TI-84, please actually check in with me because you might be able to shortchange this a little bit. You might have a feature on the calculator that allows you to bypass doing this change of base formula here. So one way or the other, though, we need you to get to be able to evaluate a logarithm in any base. And so if you have a TI-83, you're going to have to do the change of base formula, and it goes log of the input divided by log of the base. That's this piece right here, and that's exactly what I found when I did log base 2 of 7. For those who have the TI-84, again, please just check in with me. I can take a look on your calculator and see if you have that feature that allows you to just type it in as is and get the answer. All right, cool. So last piece, and actually I would love for you to pause the video in just a moment and run through all 12 and see if you can go 12 for 12 on these. So let's see if you can understand these properties without using a calculator. Can you just look at them and decide if they are true or false? So pause for a moment if you would, and then let's see how you did. All right, well, here's how we started out. So this definitely is the product property. Log of 3 plus log of 6 is log of 3 times 6. True. This, guys, is not true. Log of 3 plus log of 6 is log of 3 times 6, not 3 plus 6. So false on that one. All right, let's see this one over here. So this is definitely the quotient property. I can subtract these two logarithms by dividing the inputs. 16 divided by 4 is 4. Definitely true. All right, good. I go over to letter D. Same deal. 16 and 4. Again, this is the quotient property. So I'm supposed to divide these right here. So this one is false. Again, this would be log of 16 divided by 4, not 16 minus 4. Okay, we saw this during the lesson. Can I expand this out? Is there a sum property? Absolutely not. Again, showed you numerically that does not work. So false on that one, leave it exactly as is. Same deal, there's just no way to expand a sum or a difference into different logarithms. And so as a result, this one is false too. All right, I love making that distinction. Make sure you kind of see it. All right, here we go. Product property again. Log of 2 times x is not log of 2 times log of x. Officially, this would have to be a plus. Product property means you add the logarithms together. Okay, same deal here, guys. This is what we would say the quotient property. This would be log of x minus log of y if I was to do this. So this one obviously is false. Sorry about that. So in this case, false again. Definitely not working. All right, letter I. Can we take that x and bring it on up? Most definitely. That is the power property in action. So there is true for letter I. Here we go, letter J. Does that look like your great stereotypical quotient property? Most definitely. Log of x minus log of 2. So true on that, quotient property in place. This one showed you above. Remember, think of this as a negative 1 out in front. It goes up here and becomes x to the negative first. How do I deal with the negative exponent? I bring it on down, make it positive. And so that's what we talked about before. A negative in front of the logarithm, the term goes to the denominator and makes it positive. So definitely true right here. That's a good one. And then last but not least, does this look like the change of base formula? It sure does. Log of the inputs divided by log of the base. And so true on that. So curious how you did. 12 good ones right there, really just playing around with it. what works on logarithms and what does not. Hey, thanks for listening to the lesson there. Let me know if you have any questions.